Welcome. My name is Bob Tickleman. I'm a Microsoft technical trainer, and I'm excited to be your guide to this delivery of what you want to know when you want to know it. In this module, we'll look at operational excellence in the context of DevOps and how it can be achieved through practices such as continuous operations, continuous monitoring, health modeling, reliability engineering, incidents management, security integration, shift right testing, observability, performance monitoring, and security monitoring and assessments, site reliability engineering, and platform engineering. Additionally, we'll look at how to minimize downtimes, proactively detecting issues, increasing resiliency, effectively responding to incidences, integrating security, and test features in production environments. Let's get into it. Operational excellence is a key pillar of the Azure well-architected framework, and it focuses on ensuring that your workloads run reliably and predictably even during times of change. We'll dive into specific areas of continuous operation, continuous monitoring, observability, health monitoring, and reliability engineering. Operational excellence involves the continuous improvement of processes and practices to ensure that your systems run reliably, efficiently, and resiliently. It emphasizes the importance of collaboration, shared responsibility, and automation to achieve high-quality outcomes. Continuous operations is about maintaining the continuity of your services without interruptions. This involves automated processes to reduce the need for manual intervention and ensures that your systems can handle changes and updates seamlessly. Imagine you're running an e-commerce platform. Continuous operations ensure that your platform remains available and responsive even during peak shopping times or when deploying new features. Automation tools help manage deployments, scaling, and failover processes to minimize downtime. Continuous monitoring involves the ongoing collection and analysis of data from the systems and to detect issues to ensure the optimal performance. It provides real-time insights into the health and performance of your applications and infrastructure. For a cloud-based application, continuous monitoring can track metrics such as CPU usage, memory consumption, and response times. Alerts can be set up to notify the operations team if any metrics exceed predefined thresholds, allowing for quick response to potential issues. Observability is the ability to understand the internal state of your systems based on the data they produce. It goes beyond monitoring by providing deeper insights into the behavior and performance of your applications. In a microservice architecture, observability tools can help trace requests as they flow through different services, identifying bottlenecks and diagnose issues. This enables teams to understand the root cause of problems and improve system performance. Health monitoring focuses on assessing the overall health of your systems and ensuring they are operating as expected. It involves checking the state of various components and services to detect and address issues proactively. For a web application, health monitoring can include regular checks on the availability of web services, database connections, and third-party services. If any component is found to be unhealthy, automated actions can be triggered to restart services or switch to backup resources. Reliability engineering is the practice of designing and maintaining systems to be reliable and resilient. It involves implementing best practices such as redundancy, failover mechanisms, and disaster recovery plans to ensure that your systems can withstand failures and continue to operate. In a financial services application, reliability engineering ensures that critical transactions are processed without interruption, even in the event of hardware failures or network outages. This can be achieved through techniques like data replication, load balancing, and automated failovers. Operational excellence in DevOps is about continuously improving your processes and practices to ensure that your systems are reliable, efficient, and resilient. By focusing on continuous operations, continuous monitoring, observability, health monitoring, and reliability engineering, you can achieve high-quality outcomes and provide a better experience for your users. As explained in another module in this learning path, testing and application lifecycle management is essential to maximizing code quality and minimizing operational risks associated with deploying and updating software. This is the reason for applying the shift-left approach, which introduces testing activities as early as possible in the development phase. However, there are certain aspects of testing which aren't effective when carried out in this manner. Instead, to fully serve their purpose, they need to be performed in the production environment. This is referred to as shift-right approach, or sometimes called testing in production. Shift-right testing involves performing testing activities in the production environment to validate the behavior or performance of application under real-world conditions. This approach complements shift-left testing, which focuses on early testing in the development lifecycle. Microservices architecture involves deploying multiple independently managed services that work together to form an application. Shift-right testing is particularly important for microservices because it allows you to test the interactions and the compatibility of different services in the production environment. This helps ensure that new versions of services do not introduce issues when deployed alongside existing services. Imagine you have a microservice-based e-commerce platform. By deploying new versions of individual services to production and monitoring their interactions, you can identify and resolve compatibility issues that might not be apparent in a staging environment. User acceptance testing, or UAT, is a critical phase where end users validate that the application meets their requirements and works as expected. Shift-right testing allows us to conduct UAT in the production environment, providing users with a realistic experience and ensuring that the application performs well under actual usage conditions. For a new feature in a customer-facing web application, conducting UAT in production allows real users to provide feedback on the feature's usability and performance. This helps identify any issues that might not have been detected during earlier testing phases. Network latency can significantly impact the performance of an application, especially in distributed systems. Shift-right testing involves evaluating the impact of different network latency conditions on the application in the production environment. This helps ensure that the application remains responsive and performs well under varying network conditions. For a video streaming service, testing the impact of network latency on video playback quality and buffering times in production helps ensure a smooth user experience, even for users with slower internet connections. Redundant configurations are designed to ensure high availability and reliability by providing backup systems that can take over in case of failures. Shift-right testing involves validating failover procedures in the production environment to ensure that the system can seamlessly switch to backup resources without disrupting the user's experience. For a financial services application, testing failover procedures in production ensures that critical transactions can continue to be processed even if the primary database server fails. This helps maintain service continuity and reliability. Shift-right testing in DevOps is essential for validating the behavior and performance of applications under real-world conditions. Observability is a key aspect of ensuring that our systems are running smoothly and efficiently. It allows us to understand the internal state of our systems based on the data they produce. We'll focus on three critical metrics: time to detect, time to mitigate, and time to remediate. Time to detect refers to the amount of time it takes to identify that an issue has occurred in a system. This is the first step in the incident response process. The faster we can detect an issue, the quicker we can begin to address it. Imagine you're running a web application and a sudden spike in response times indicates a potential issue. With effective performance monitoring tools in place, such as Prometheus and Grafana, we can quickly detect this anomaly and trigger an alert. This immediate detection allows your teams to start investigating the root cause without delay. Time to mitigate is the time it takes to reduce the impact of an issue after it has been detected. This involves implementing temporary fixes or workarounds to minimize the disruption to users while a permanent solution is being developed. Continuing with the web application example, once the issue is detected, your team might implement a temporary fix, such as redirecting traffic to a backup server or scaling up resources to handle the increased load. This mitigation steps helps to stabilize the system and reduce the impact on the users while the underlying issue is being addressed. Time to remediate is the time it takes to fully resolve the issue and restore the system to its normal state. This includes identifying the root cause, implementing a permanent fix, and verifying that the issue has been resolved. After mitigating the immediate impact, your team conducts a thorough investigation to identify the root cause of the performance issue. This might involve analyzing logs, traces, and metrics to pinpoint the problem. Once identified, a permanent fix is implemented, such as optimizing a database query or fixing a bug in a code. The final step is to verify that the issue has been resolved and that the system is performing as expected. Observability through performance monitoring is essential to maintaining the reliability and efficiency of our systems in DevOps. By focusing on time to detect, time to mitigate, and time to remediate, we can ensure that issues are identified and resolved quickly, minimizing the impact on users and maintaining a high level of service quality. Observability is crucial for understanding the internal state of systems and ensuring that they are secure and resilient. We'll focus on three key topics: wargame exercises, live site penetration tests, and secure monitoring and security assessments. Wargame exercises are simulated attack scenarios where two teams, typically referred to as the red team and the blue team, test the security of a system. The red team acts as the attackers, attempting to exploit vulnerabilities, while the blue team defends against these attacks. These exercises help identify weaknesses in the system and improve the overall security posture. Imagine your organization is preparing for a potential cyber attack. By conducting a wargame exercise, the red team attempts to breach the system using various attack vectors, while the blue team responds in real time. This exercise helps uncover vulnerabilities and provides valuable insights into the effectiveness of your security measures. Live site penetration tests involve authorized security professionals actively attempting to exploit vulnerabilities in a live production environment. These tests simulate real-world attacks and help identify security gaps that might not be apparent during regular testing. For a financial services application, a live site penetration test can reveal vulnerabilities in the authentication process, data encryption, and network security. By addressing these vulnerabilities, you can enhance the security of your application and protect sensitive customer data. Security monitoring involves continuously observing the system for signs of security threats and anomalies. This includes collecting and analyzing logs, metrics, and other data to detect potential security incidents. Security assessments, on the other hand, are periodic evaluations of the system's security posture, including vulnerability assessments, configuration reviews, and compliance checks. For a cloud-based application, security monitoring tools like Microsoft Defender for Cloud can provide real-time alerts for suspicious activities, such as unauthorized access attempts or unusual network traffic. Regular security assessments help ensure that the system remains compliant with security standards and best practices. Observability through performance security assessments is essential for maintaining the security and resilience of our systems in DevOps. By focusing on wargame exercises, live site penetration testing, and security monitoring and security assessments, we can proactively identify and address security vulnerabilities, ensuring that your systems are robust and secure. Site reliability engineering, or SRE, is the discipline that applies software engineering principles to infrastructure and operational problems, aiming to create scalable and highly reliable software systems. SREs enhance resiliency in DevOps environments and is a role that is gaining prominence within the industry. We'll focus on defining service level objectives, or SLOs, establishing service level indicators, SLIs, and service level agreements, SLAs, and setting up error budgets. Service level objectives, or SLOs, are specific, measurable goals that define the desired reliability and performance of a service. They are crucial for setting clear expectations and ensuring that the service meets the needs of its users. SLOs are typically expressed as percentages, such as 99.9% uptime, or 95% of requests must be processed within 200 milliseconds. For an online banking application, an SLO might be defined as 99.99% availability, meaning the service should be available 99.99% of the time. This helps ensure that users can access their accounts and perform transactions reliably. Service level indicators, or SLIs, are metrics that measure the performance and reliability of a service. They provide the data needed to evaluate whether the service is meeting the SLOs. Common SLIs include response times, error rates, and system throughput. Service level agreements, or SLAs, are formal agreements between service providers and customers that define the expectation levels of the service. SLAs are often included with penalties for failing to meet the agreed upon SLOs, providing a strong incentive for maintaining a high service level quality. For a cloud storage service, an SLI might be the average response time for file uploads. The SLA, on the other hand, specifies that the service will maintain a 99.9% uptime, with financial penalties if the target is not met. This ensures that customers will receive reliable service and have recourse if the service fails to meet the expectation. Error budgets are a concept in SRE that help balance the need for reliability with the need for innovation and change. An error budget is the allowable amount of downtime or errors within a given period based on the SLOs. It provides a quantifiable limit for acceptable risk and helps teams make informed decisions about deploying new features or changes. If the SLO specifies 99.9% uptime, the error budget allows for 0.1% downtime. This means the service can be unavailable for up to 43.2 minutes per month. If the error budget is exhausted, the team must focus on improving reliability before deploying additional changes. This approach ensures that reliability is maintained while still allowing for innovation. Resiliency within site reliability engineering in DevOps involves defining clear service level objectives, establishing measurable service level indicators, and formal service level agreements, and setting up error budgets to balance reliability and innovation. By implementing these practices, we can create scalable, reliable, and resilient systems that meet the needs of our users. Platform engineering can significantly improve the developer experience in DevOps. Platform engineering focuses on building and maintaining the underlying infrastructure and tools that developers use to build, test, and deploy applications. We'll cover the 4 areas of enhancing the developer experience, ensuring security and compliance, creating a seamless and intuitive environment, and providing tools and resources. Enhancing the developer experience is about making it easier and more enjoyable for developers to do their work. This involves reducing friction, minimizing cognitive load, and providing a streamlined workflow. By implementing self-service capabilities, developers can quickly provision the resources they need without waiting for manual approvals. This not only speeds up the development process, but also empowers developers to take ownership of their own work. For instance, a developer can use a self-service portal to spin up a new developer environment in minutes, allowing them to focus on writing code rather than dealing with infrastructure. Ensuring security and compliance is critical in any development process. Platform engineering helps by embedding security and compliance checks into the development workflow, making it easier for developers to adhere to best practices and regulatory requirements. Automated security scans can be integrated into the CI/CD pipeline to check for vulnerabilities in code and dependencies. Compliance checks can ensure that code meets the industry standards or organizational policies. For example, a financial services company can use automated tools to ensure that all code changes comply with PCI DSS requirements before they are deployed to production. Creating a seamless and intuitive environment involves providing developers a cohesive and user-friendly interface for all their development requirements. These include integrating various tools and services into a single platform that developers can easily navigate. A unified developer platform can provide a single dashboard where developers can access their code repositories, CI/CD pipelines, monitoring tools, and documentation. This reduces context switching and makes it easier for developers to find the information and tools they need. For instance, a developer working on a microservice application can use the platform to monitor the performance of their services, view logs, and deploy updates without leaving the dashboard. Providing developers with the right tools and resources is essential for improving productivity and ensuring high-quality outcomes. Platform engineering involves selecting, integrating, and maintaining the tools that developers need to do their jobs effectively. By offering a curated set of development tools, such as integrated development environments, or IDEs, version control systems, and testing frameworks, platform engineering ensures that developers have everything that they need to build, test, and deploy their applications. For example, a development team can use a pre-configured IDE with built-in support for their predefined programming languages and frameworks, reducing setup time and increasing productivity. Improving the developer experience with platform engineering in DevOps involves enhancing the developer experience, ensuring security and compliance, and creating a seamless and intuitive environment and providing the necessary tools and resources. By focusing on these areas, we can create a more efficient and enjoyable and secure development process. In this module, we defined operational excellence in the context of DevOps. Operational excellence involves practices such as continuous operations, monitoring, health modeling, reliability engineering, incident management, security integration, and shift-right testing. These practices aim to promote efficiency, resiliency, and continuous improvement in day-to-day operations. By adopting these practices, organizations can minimize downtime, proactively detect issues, and increase resiliency, efficiently respond to incidences, and integrate security and test features in production environments. One of the key takeaways from this module is the concept of shift-right testing. Shift-right testing involves testing in the production environment to fully assess the reliability of systems. This approach is suitable for scenarios such as microservice deployments, evaluating network conditions, user acceptance testing, and validating failover procedures. Another important concept is observability, which plays a crucial role in operational excellence. Observability provides insight into the operational status of systems and applications, aiding in performance monitoring, incident response, proactive remediation, and security monitoring. I hope you enjoyed this module, and I look forward to seeing you in another module.